Hello. Welcome to the virtual version of our third workshop in our advanced track. And this workshop's going to be about procedural generation and how we can get some sort of algorithm to get a randomized output so that we can use that in our game somehow. Brought to you by Christian. Hello, that is me. Here's the GitHub repo link. Everything should also be in our link tree or linked somewhere in our Discord. Feel free to go any way about to get these slides. You won't need any Unity project files for this, as everything is straight from the Unity editor with nothing else set up. Okay. This is just a bit of a topic overview. And so before we jump into code, I want to talk about just kind of what exactly procedural generation is, or what it can be, rather. There are two kind of types of randomness that we're going to talk about real quick, and it's true randomness as well as Purlin Noise, which is a sort of pseudo-randomness. And then after that, we're going to talk about its application to games that we could use. And, towards the end, we might have a bit of time for exploration, but we'll see how long it takes before that. All right, procedural generation. So, when you load up a game of like mm, Terraria or something, clearly the world is not the same every time you create a new one, and the world needs some sort of randomness. Each generated element in a game must be unique up to a certain extent um, in order to create a replayable game. If everything was static, there might not be as much replayability. Of course, there are games with like, branching storylines or like there is replayability, but in the case of a bunch of roguelikes, which I'm a fan of, as well as like just like open world sandbox games, you're gonna need to somehow randomly generate and create worlds. And what are the best ways to retrieve this randomness? True randomness. All right, so this is one of the ways we can retrieve some sort of random value to help us create that world. And as you can see here on the right, each element is pretty much generated independently, regardless of its neighbors. And this kind of creates a very, very like chaotic image. They use the word noise to describe it. And it's pretty accurate because, everywhere you look, it's kind of visually noisy. Right here, like you can see a lot, like there's white, then black, then white, black, and white. There's kind of no gradient, and each element is kind of distinct if you zoom in enough. This sort of true randomness is really good when you try to work with invisible stuff that happens behind the scenes. Some examples are like, what if your Pokemon wants to crit? You can just kind of generate a random value, and if that random value is like greater than or less than a certain value, like a certain predetermined crit chance, then you can say, hey, that's a crit. Um, However, this looks messy when visibly affecting the player, and like, putting this on some sort of like texture would not look very good in your game. And so that's where we come to pseudo-randomness. Pseudo-randomness, as you can probably tell, is not true randomness. As you can see here on the right, it's labeled Perlin noise because it's using some sort of mathematical function to generate uh, this image or the values pertaining to this image. Um, and pseudo-randomness is not true randomness because each element is generated in relation to its neighbors. As you can see here, um, it is very fuzzy to look at. No, your eyesight is not going bad. No, it's not 240p. This is simply how the image looks. As you can see, there's like white right here, and then it slowly has a gradient toward black. And so what that means is every pixel in this image is kind of generated in relation to the other pixels nearby it, so that like we'll call it the color for now. The color of of that location is similar enough to the others, but different at the same time. And so this is a lot better for generating visible stuff, such as terrain or textures, etc. And these gradual changes allow for a quote unquote better generation that's a little more friendly to the player. For example, if we were if we were going to use how dark a location is as the height of like a randomly generated prairie or like set of hills, um, this is much more of a gradient. So like you'd see a gentle slope towards like the peak of the hill and then the bottom where the white is. In contrast, if we were to look at true randomness, you'd see peak here and then immediately kind of like the valley, peak, valley, peak, valley. It's a lot more chaotic, and maybe the player wouldn't be able to go up and down these harsh steps. Okay. Now that we kind of talked about what we're going to use, now that we kind of talked about true randomness and pseudo randomness, we're going to kind of say, hey, how can we apply this to a video game? Just to back up a bit more and talk about procedural generation again, is the intention of procedural generation is to use some sort of algorithm to procedurally generate some sort of world or element in a game or anything of the sort, such that every time you load it up, it's a bit different every time, but at the same time, there's some sort of behind the scenes algorithm that controls it. And so now we're going to go on to the hands-on portion, where we can kind of code up and see how to use this in the Unity engine. All right. So here we're just going to be in a Unity 3D scene, with nothing in it besides, the default camera and directional light. So go ahead and create that. Also, all the code that I'll be referencing, you could either follow along as I code it on this screen, or of course, there are slides available, and I'll kind of show that to you as we go. But yeah, to begin with, we're gonna kind of see how randomness could be used to generate textures on an object. One example of how textures might be randomly generated during a game is, we'll use Pokemon Go for an example. The Pokemon Spinda has classically been loved in the Pokemon community for having a randomly generated texture where the spots on it are different for every single Pokemon. This one here got a little goatee, and then this one here got a little blush. So you can see that there are very popular games where textures can be randomly generated. So the way we're going to implement that is going to be creating a 2D quad within our scene. So we're going to go ahead and go to Game Object, create 3D Object, Quad, and we can go ahead. As you can see, whenever you do this, um, pro tip, whenever you create something, always reset the transform, because right now the transform is in Narnia. We don't want that, so we're just going to go ahead and bring that to 0, 0, 0, 0, 0 technically. And then we are going to go ahead and give it a scale of 8, 8, 1, so it's a little bit bigger. Um, and so, yeah, so this is going to be our object that we are going to place a texture on. Next, we're going to create a script on this quad object, and we're going to go ahead and call it Purlin Noise, as that's the pseudo-randomness that's how we're going to procedurally generate this texture using pseudo-randomness. And really quick, to dip back into Perlin noise, in case you're curious, Perlin noise is, it's not technically like a Unity thing or game dev thing, or anything of the sort. It's sort of this mathematical function that's been invented by somebody for realism. As you can see here, the original intent was to kind of like increase realism in computer graphics, and so, that's what we're going to be doing right now. And so this is an organic surface generated with Purlin noise. So this is all like cool math stuff. To be honest, I don't fully understand like the ideas behind it, but I can explain its application since it's a very math heavy thing. So yeah, we have our Purlin noise script, and through this script, we're going to kind of place this image onto here in some sense. While it won't be exact, we will be using that. All right, let's just go ahead and open up this script. All right, Purlin noise. So for now, since we are defining a texture, let's just go ahead and define some variables for said texture. And we're going to say a public int width equals 256, public int height equals 256. This is going to represent a 256 by 256 pixel canvas for us to draw on for said texture. And in this start function, we're going to go ahead and find the renderer of this object that we're attached to. And we're going to do that by doing get component renderer. And then we're going to go ahead and say render.material.main texture goes generate texture. Okay. Real quick to explain this part, get component is a pretty common way of grabbing the component of a game object that this script is attached to. And so as you can see here, the script is attached to this quad object, and this quad object has a mesh renderer. And so we will retrieve that mesh renderer through um, this thing right here. And the render allows us to see it on the screen. And so what we want to do is this render has a material, and that material has a texture, and we want to modify that texture. So we have this placeholder function right here called generate texture, and we'll sort of fill that in as we go. Cool. And so what I'm thinking right now for the main idea behind generating a texture is that since we have a 256 by 256 canvas, what we could do is go ahead and just create a new texture and then individually paint each pixel based on our Purlin Noise function. Um, and so what we're gonna go ahead and do, we'll skip this update for now, is we're gonna have a private texture 2D, since that is what we need to assign this main texture. Uh, we're going to do private texture 2D, generate texture as we typed just up there. And this isn't going to take any sort of parameters for now, because this function um, will simply be based on the Unity engine's Purlin Noise function, which I'll get into in just a moment. So yeah, what we're gonna do here is we're gonna define a new texture, uh, new texture 2D height. So here we're gonna go ahead and just instantiate a blank texture, or an empty texture rather, with this canvas size. And what we can do here is that we can individually set the pixels of this texture um, using this thing called texture.setPixel. And as you can see here, it's a void function that takes in two integers as the x and y location of the texture, and then a color. And so since you want to kind of individually paint each pixel according to however our randomness is going to go, we're just going to go ahead and say for int I equals 0, I is less than with I plus plus, and then we're going to say the same thing but using j. And so what we can do here is now we're going to go ahead and take this texture.setPixel, um, and we'll say ij, and what we still need to do here is figure out the color. And so for now, this is going to remain undefined, but I'll just double back to the presentation really quick. As you can see here, we kind of want to recreate this texture using Unity. Or sorry, recreate this image using Unity. And so what we want to do here is we kind of want to retrieve this Purlin noise um, and use this Purlin noise function um, as the values of each pixel, such that like if this was x equals 0, y equals 0, it would be like a black. But then if this was x equals 1, y equals 1, like right here above my cursor, it would be a white. Uh, and so on and so forth, such that this is like 256, 256 right up here. So how are we kind of gonna retrieve this Perlin randomness? So I'm gonna go here. What I'm gonna do here is search up the documentation and show you guys real quick. Unity has documentation and API over on their website, and it's always wonderful to refer to in case you're kind of confused on what to do. And so here we have mathf.purlinnoise. Mathf is going to be their math library that really helps with all that jazz. And it's going to return a float value, as you can see, between 0 and 1. Um, and so what happens here is that this function is intended to generate a 2D Perlin noise pattern. Um, so as you can see here, Perlin noise is a pseudo-random pattern of float values generated across a 2D plane. Um, I mentioned this earlier, how it's like kind of generated in relation to its neighbors. And so that's why it's kind of like fuzzy and there's always a gradient. So we are going to go ahead and use this mathf.purlinnoise function in our own script. And so what we'll do here for now is we'll just say color equals generate color ij. Uh, and yes, this generate color function isn't quite created yet. But the idea behind this is we want to separate the logic of creating a color from the texture so that it would be easy to change like how we generate the color without kind of fiddling with our texture logic. Um, so yep, that's what we're going to do right here. We're going to go ahead and create a private. Uh, we're going to go ahead and create a private function and we're going to call it generate color and it's going to return a color. And what we're going to do here is we're going to sample uh, the Purlin noise function at this location that we're getting passed. So as you can see here, mathf.purlinnoise, it's already in the library, and just to return to the documentation, this picture is sampled in the range of 0 to 10. So like, this would be x equals 0, y equals 0, and then this would be uh, x equals 10, y equals 10. And so, yes, any point in the plane can be sampled by passing appropriate x and y coordinates. So, yeah, what we're going to do here is just store this into a value. We're going to call it Perlin sample. And we need to use this Perlin sample to create some sort of color. And for now, we'll go a little bit simple and just say uh, return new color, Perlin sample, Perlin sample, Perlin sample. So this is just going to create a color between white and black, since all the values are equal. And so now we're kind of all set here, and we've already figured out the logic to generate the color based on the location, and we set the texture pixel to it. And after we kind of set the pixel um, at every point, what we're going to do is we also need to say texture.apply to fully apply it to the texture. This is just something with Unity, not really related to anything of random generation. And then we're going to go ahead and return this texture since we need to use it in this in this start function. Cool. And we should be good to go. Hopefully this compiles and we'll try running this. And we now have a gray box. This is not interesting. Um, and so, I made a mistake in the code that I kind of left in. And, I'll give you just a little bit. You can refer to documentation if you want to try to fix this yourself. But yeah, I'll give you like 5 seconds or like 10 seconds to see if you can find the bug in the code in terms of why the values that it's getting set are all the same. Okay, so why do we currently have um, this issue? And so, um, what happened here is we currently have an issue of floats versus integers. So as you can see here, this Purlin Noise function takes in an x and takes in a y. And what we kind of have realized is, so what we have now kind of seen is that our generate color function actually takes in an x and takes in a y as integers. And, this doesn't quite work with what we want. Um, the Perlin noise function, although it's a little difficult to find it in the documentation, actually repeats itself on whole numbers. And so that is why when we click play right here, every single pixel is the same value. And we don't really want that. So what we're gonna do is we kind of need to convert this into an interesting float. And so the way we can do that is we can sample the Perlin noise from 0 to 1 by dividing this x by the width and dividing the y by the height. This gets us a value between 0 and 1. And so we're going to go ahead and try that. So yeah, so now these coordinates, instead of being, 0, then 1, then 2, then 3, then 4, and, these big jumps of whole numbers, what we're going to do now is now we're going from 0 to 1 over 256, 2 over 256, 3 over 256, etc., etc. And these smaller values are going to allow us to kind of get this a little bit better since, the Perlin noise function, maybe we're jumping too far if we jump by ones, and thus we're getting repeated values. Um, okay, so yeah, let's go ahead and try this out. Okay, so yeah, this still is not quite interesting enough. It seems that there is still an issue with the way we're grabbing our random values. And so to potentially clue us in as to what this issue might be, as we can see here, our texture does not currently look like this. It's all one value. So perhaps maybe we are a little bit too zoomed in. And so what we're going to do now is we're going to try to kind of scale these coordinates in order to properly look at this Perlin noise 2D plane that Unity is providing us. So right now, if I were to go back to the documentation, Unity is providing this 2D plane, and maybe we're just zoomed too far in to notice any noticeable change. So what we can try to do to fix this is we can kind of scale these coordinates to properly look at the rest of the plane. And we'll go ahead and define it right here for the sake of ease. And let's go ahead and do this, public float scale. And so now let's try this. Okay, sorry, we're going to rewind to right around here where we cast it into floats. All right. All right, and along with the repeated Perlin noise, making it so that sorry, making it so that we kind of don't get interesting values. What we also need to do that I kind of forgot to mention earlier is um, changing this object to kind of be an unlit object because we don't want it to rely on light at all. So what we're going to do here is we're going to go ahead and quickly create a material. We won't get into kind of what a material is too much, but just know that it will allow us to kind of work our way around the lighting system. So we're going to go ahead and call it an unlit texture. And we are going to, all right. Okay, so earlier we had, you know, our earlier version, we were just using the X and the Y um, directly. And so just to kind of rewind a bit, what we were doing just before we kind of added this right up here is we were using X and Y directly, but we kind of don't want to do that anymore um, because we want this all to we want to kind of make smaller jumps based on the height scale to the height and the width of this. And notably, we casted x to a float and casted y to a float, so that the stepping of this x coordinate every time the x increases, or the y coordinate every time the y increases, is much more kind of incremental rather than large whole number jumps where it might repeat. Okay, and so notably right here, real quick, what I forgot to mention earlier is we want to create a new material. I'll just redo this real quick. Delete. Okay, so what we want to do is to remove our dependence on this light because we don't want it messing around with any of our values. We're just going to go ahead and create a new material right here, and we'll just call it unlit, and we're going to go ahead and change the shader type of it to unlit texture. And we're just going to go ahead and apply that to our quad. Here we go. And now it won't rely on lighting at all. As you can see, it's like very bright right here, even though there is no light in the scene. And this is what our texture now looks like. As you can see here, we definitely are picking up somewhat from this kind of plane right here. But it's kind of still not that interesting. Um, but the general idea is there, and we really are getting some sort of pseudo random value to create this text right here. So what we're gonna do now is, since we kind of are getting this, but it's not quite looking at it like this, it kind of seems like we're a bit too zoomed in to get the full picture of this plane. And since we're kind of too zoomed to get the full picture of this plane, what we can do is we can kind of go back to our code and we can scale these x coordinates and y coordinates so that every time x and y increase, the x coordinate and y coordinate increase by a little bit more than just 1 over 256. This will allow us to see more of the picture because instead of, like, for example, if this was 0 to 1 right here or something, uh, we could scale it so that we're instead looking at 0 to 3 by 3. And so the way we're going to do that is we're going to go ahead and multiply these coordinates by scale. Yes, scale is undefined right now. So what we're going to do here is define a public int scale equals, call it 4.0f or 3.0f. So we're going to set the value to, sorry, we're going to make this a float. So now we have a float value of 3f. F is just to denote that it's a float. And so let's try that. See if this allows us to see more of the 2D plane. And there we go. As you can see here, it makes a lot more sense right here than um, than what we had earlier. In fact, it's a little too grainy. It kind of looks like the random function. So what we can do here is we're just gonna go ahead and kind of change it back to a 2F to reach a happy compromise, and let's see how that looks. Oops. Oh, sorry. Right here, um, what I didn't realize is that this is my right here, sorry, the default of the scale got set to 100, which is why it was so grainy. So we're actually going to set this to 3. Going to set this to 3 outside of play mode, and let's see what this actually looks like. And here we go. So yeah, this is clearly, we're seeing more of the image. And if we set it to a 20, um, then we're gonna see something like this, where it's definitely like there's gradients between the blacks and the whites, and it's not entirely random. Um, so yeah, I don't know why this set itself to 100 earlier, even though I put like 3F here, um, but it's all good. So yeah, and one quick thing that we're gonna do to play around with this a bit more is, sorry, let me just take the time real quick. Um, we're going to go ahead and allow this to change itself uh, every frame. So we're just going to go ahead and copy paste this stuff. We're going to move this renderer to right up here. Um, just to allow it to get accessed elsewhere. And we're going to go ahead and do this. Okay, so what I just did here is I moved this to be, instead of a function variable, I made it a class variable. And this allows us to access renderer within the update function as well. And so what we're going to do here is we're going to kind of take another look at the Purlin Noise plane. And as you can see here, we are at a scale of 20. But now that I have it in update, we can kind of move this scale so that we can zoom in. And as you can see here, this is what we initially had. And uh, now we have all this information to look at. So as you can see, the further you zoom out, the more random it looks. The further you zoom in, the less random it looks because everything is in relation to the other. Okay, and now I'm going to take this time to kind of address something that one of uh, one of my lovely interns mentioned to me when I first presented this tutorial live. As you can see here, let's have a scale of 2 and boot up the game. Boom, it looks like this. And if we go here again and click play again, boom, it still looks like that. And this is an issue because, this isn't random. Um, as I mentioned earlier, the Purlin noise is a already predetermined plane that Unity is providing to us. And so even though, yes, it's great that we're getting these values that are kind of very close to each other but different, where, this is like a value of like 1, this is a value of 0, and in between here are values going from 0 to 1 gradually. That's great and all, and we can use that. But it's not quite random. And as you can see here, if we imagine this as like the Spinda example that I mentioned earlier, all the Spinda Pokemon textures are the same. And so that's not quite interesting. But as you can see from the documentation, they kind of said right here, the same coordinates will always return the same sample value, but the plane is essentially infinite, so it is easy to avoid repetition by choosing a random area to sample from. What we can do here is we have this generate color function, um, and we're always kind of looking at the same place every time we boot up the game. The way we could change this is by creating some sort of offset. And so for the sake of some simplicity, I'm just going to go ahead and define a single offset for both the x and y values, and we'll call it random offset, uh, and we'll have it be a float. And within our start function, we're going to go ahead and assign this random offset on play to mathf dot ran sorry, I think it's random dot range, and we'll do 0 to 1. And what we're going to do with this 0 to 1 is we're going to use this, we'll actually do like 0 to 100, 1000. And so what we can do here is we can add this random offset to our coordinates so that every time we click play on our game, it'll run this line of code and get a new value every time we play the game for a different time. And we'll kind of like teleport ourselves to a separate section of this 2D plane that hopefully has never been looked at. So let's just go ahead and see if this works. Okay, cool. Okay, sorry. So yes, earlier we added the offset to both the x and y. Um, but I used the wrong function. And so instead of using random.range, we're going to go ahead and use random.value times scale. So what random.value is going to do is it accesses the Unity Engine's random library and then return a random float within 0 and 1. And then we'll multiply that by our scale um, to hopefully, get a different section based on how much we're already looking at. Um, so yeah, just to test if this is working. So kind of remember this image in your head. And now I'll click play again. This image is still the same, but if we click play again, we get a different image. And so earlier the image that loaded was probably the same because Unity didn't change its seed just yet. But now, as you can see here, this is different than when we'll click play again, uh, than this image right here. Um, or at least I think they're different, unless I'm going crazy. Okay, so yeah, uh, earlier, as I mentioned, when we kind of look at the same x and y coordinate, we always get the same Purlin noise value. And so the way we could allow for true, like a bit more randomness, is we sample different sections of the Purlin noise function. Basically, if like our first run of the game, we kind of look at 0 to 10 by 10 of the Purlin noise function. Hopefully, the next time we click play, we can look at 120 by 120 to 130 by 130. And this will allow us to see values that, we've never seen before. And so this is a way to alleviate the pseudo randomness value and create a more randomized look. Even though it's truly like we know that there's like this sort of 2D plane that has all the information already, it's so expansive that it basically is random. And actually, this is how a bunch of other systems use it too, or utilize randomness as well. For example, in Verilog, if you use the randomness values of the board, it kind of just takes the first bit of a clock value, and that clock value moves so fast that it's basically random whenever you sample it, but it's not actually randomness. So this kind of fake randomness is a common factor in a bunch of random generation. Okay, and so now I guess one last thing to explore this texture thing before we move on. Let me check the time real quick. Um, what we can do here is we can modify our code to also have a random offset every time, just to display this randomness just a little bit more. And so we'll just go ahead and try this. So as you can see here, it's a bit odd to look at, but if we click pause several times, you can see that this pretty much always shows a different section whenever we pause. Sometimes you see the same thing or roughly the same thing, but most of the times it's different enough from the last time that it would be a noticeable change. So yeah, this is how we create a texture. Uh, and another way we can kind of like alleviate the fact that, this is all the same plane. Maybe we want to explore this plane a bit more. We can define x offset equals 0.0f and then y offset equals 0.0f. Um, and then also add these offsets to coordinates. And we're just going to go ahead and comment this out for now because I don't want that anymore. And so let's try this. So now we're kind of in this random location of the plane, and we can zoom out a bit using the scale. We'll leave it about 10 or exactly 10. And then this x offset clearly allows us to kind of travel along the plane, and so does the y offset. So by a combination of scale, x offset, and y offset, we can kind of create um, this exploration of the 2D plane that allows us to find new pseudo-random values every time we play. Maybe we could randomize the scale, maybe we could randomize the x offset, y offset individually, maybe we could offset them together. There's tons of stuff you can do in order to access this vast plane of information. So yeah, now we're going to move on to kind of creating a landmass using Purlin Noise. So just we can double back. Feel free to double back to the notes or the presentation rather. Um, yeah, we're going to go ahead and disable this quad, and we're going to go ahead and turn on my lights because it's dark. And then we're going to go ahead and create a game object and 3D object and terrain. So we're going to be moving a bit faster now that I kind of explained the ideas of like how pseudo-randomness works as well as Purlin noise. And so now, we have this very chonky landmass terrain for the Unity engine. They provide it and it already has like colliders and everything. Um, so what we can do here is just like um, just like how we did the texture generation, we can kind of individually select um, each kind of pixel here or sorry, rather than pixel, we're going to use the term vertice or vertex. Every vertex of this texture, we'll call it like maybe this is 0, 0, and then that's 256 by 256. So we could kind of pick the height of every vertex and use that, uh, sample the height using Perlin noise, and then set the height to be that Perlin noise sample, so that it kind of like has a pseudo-random look to it for the height. And as I mentioned earlier during my slideshow presentation, it'll kind of look like valleys and hills, with hopefully enough gradualness such that the player would have ease in climbing it. Uh, yeah, this is unlike Skyrim where, there would be a giant mountain and for some reason I would just walk into uphill slopes until I found that weird buggy spot where I could kind of ascend myself. We kind of want to try to avoid that and just have it be a lot more natural to walk up the slopes. Cool. So what we're going to do here is we're going to go ahead and add a script and we'll call it terrain generator. Create an add. And a lot of the stuff that I'm about to talk about can just be found in the terrain documentation for Unity. It's not really random generation related, so I'll probably avoid talking about it too much. So yeah, what we're going to do here is we're going to do the same as Purlin noise, where we kind of define these right here. A width and a height. These are kind of arbitrary values based on how many vertexes or vertices we want on the terrain. And we're gonna go ahead and say terrain equals get component terrain, uh, and then we'll say terrain dot terrain data, equals generate terrain. This is similar to how we had start, be get component render, and then we generated a texture. We kind of want to make sure to separate the logic of things so it's easy to tweak things. Okay, and what we're gonna do is generate this terrain. And so now we need a terrain data. So terrain data is a terrain data object, and it stores like a whole bunch of stuff about the heights and such of each vertex of a terrain. And so we're gonna say terrain data, uh, generate terrain, terrain data. So notably, what I forgot to mention here is we're actually going to use this terrain data, this initial terrain data to help us generate the next one, so that we can kind of keep some of the information. Um, okay, so what we're going to do here is we're going to say terrain data dot size equals new vector3 width uh, I'll say width 1 and height. Um, and then I'll explain the one in just a moment. And then we're also going to have terrain data dot set heights. Okay, so yeah, and then one last thing is return terrain data. So yeah, we're just going to rewind real quick and explain some of this. As I mentioned earlier, a lot of this comes from the Unity terrain engine. Um, and the terrain data class, as you can see from the documentation, stores the height maps, detailed mesh positions, tree instances, and terrain texture alpha maps. Most notably, we care about the height map. Um, and we can set the height map, or the height of each vertex of the plane, using this set heights function, which takes in an x base and a y base, and a and a 2D array of floats that kind of represent the height of each vertex. We'll ignore the x base and y base since we're leaving them to 0. Um, but this generate heights function will essentially be like, if the point 0, 0 is going to be at a height of 3, um, the array returned by this generate heights function, the 0, 0th element will also be a 3. Okay, and then this terrain data dot size is going to be the total size in world units of the terrain. So one thing that's different about this texture function, the terrain function and the texture function, is we're actually missing something. And go ahead and try to figure out what that is. It has to do with this one. Okay, what we're actually missing is we have the, width and the height of the terrain as a canvas to draw on. And that's going to be like, this is 256 and this is 256. We have the dimensions of that, but we're also kind of setting the height of this. And so since we're in 3D, we're actually going to need one more public variable, and that's going to be public int depth equals, well, we'll call it 20. Um, we need to have this terrain dot size to be the same. This value right here is going to be our depth. And I know it's a bit like odd with us calling it height right here, and then this generate heights function actually relating to a different axis. But we're going to keep it like this because, uh, earlier for our texture, we had width and height refer to our canvas. So for the sake of consistency, we'll keep width and height to relate to our canvas's dimensions, so that we can paint along it. And when I say paint, I mean set the height of each vertex. Okay, so next we're going to go ahead and generate this terrain. As I mentioned earlier, terrain data is going to store the heights at each vertex, and so we kind of need to create a float value, of a 2D array of floats that represents the height of each vertex. And notably, this square bracket comma thing is to define a 2D array. Unlike the texture thing, where we kind of go one by one, uh, actually, I'll talk about that later. But yeah, we're going to create a new 2D array that kind of has this width and height as the dimensions. And so this gives us the canvas to set the values on. And we're going to do the same thing right here as same thing as generate texture, where we kind of individually get each pixel, or each vertex in this case. And instead of color, we're just going to go ahead and say, heights. IJ equals math.f dot Purlin noise. Or actually, we'll separate this again. So again, we want to kind of separate the logic of things so that it's easier to change later on. Um, and we'll just say return heights right here. So yeah, this is a bit confusing, but this is going to be a generate heights thing, and then this is going to be generate height using I and j. And this generate height will return us a float value. Uh, and we're going to go ahead and sample the Purlin noise a pretty similar way. So we'll just go ahead and copy paste this right here. And we will exclude all this other stuff for now. So I'll just go ahead and do this. And we still sample the Purlin noise the same, except instead of returning a new color, we're just going to return the Purlin sample. And so now, hopefully, we can get a better idea of what's going on. So let's go ahead and try this. Maybe miss something. All right, so let's go ahead and take a look at this terrain in the scene. We are almost there. So as you can see here, it appears that we are kind of sampling the Purlin noise. You can tell by this like smooth gradient, but it's kind of like stopping right here for some reason. And so what's kind of going on right here is something, again, this isn't really related to the random generation aspect, but rather the Unity terrain engine that we're kind of blazing through right now. What we need to do right here in this generate terrain thing real quick is we're going to also set the terrain data dot height map resolution to something relevant to us. And that's this height resolution. If I can get that back real quick. As you can see here, the height of the text of the height map in text cells for either width or the height. Um, and we're just gonna go ahead and set this to our width because it's gonna be, for now it's gonna be the same value, or this is just one integer rather than a two-dimensional value for the x and y. It's just gonna assume, hey, this is for both. Okay, let's try this again. Yeah, all right. So just to rewind a bit, earlier we kind of were only chopping some of it up, and so now what we need to do is define this height map resolution um, to right here. Earlier I had a bug where I kind of set it down here, but it needs to be before the size and before the set heights. So yeah, that's what we're gonna do right now. And it's gonna be noticeably width plus one. And we can show what width looks like real quick, but for now, width plus one is going to allow us to have this kind of edge right here. And so, yeah, let's try it. Let's see. As you can see here, now we have a kind of, you can tell that there's like a gentle gradient that's a bit hard to see unless you kind of like see its outline. And this is a very smooth field. And so what we can do to spice it up a bit more is we can add in these things like scale, height, random offset. Uh, and so we're just going to go ahead and redefine those right here. And we'll just, for now, we'll just say private random offset equals 0.0f. And so now we can go ahead and try. We'll also move this as we did earlier. We're just going to blaze past and, kind of define this right here. And then we'll instantiate it right here. And then in our update function, we can go ahead and do this. And this will allow us to kind of explore the plane using height a bit more. All right. Cool. So now let's go ahead and take a look at scene view. And so now, not much changed. But what we can do here is we can kind of scale it so that we're looking at more and stuff actually, looks different. And so now if we have like a scale of about 13, we can see that we have these like rolling hills. And, you know, while it doesn't look like much right now, maybe we could change things later on so that maybe some of these hills could be spikier, some of these hills could be different color. But like this is basically the principle of getting some land generation using Purlin Noise. We can also like randomize it by like finding some random y offset and x offset so that it looks different every time. And we can also like make it spikier or flatter so that like, maybe the generation is different. Um, so something that was mentioned when I was running this workshop is like, this isn't too interesting using just the heights for it. But what we can do is these Purlin noise functions that are represented by heights in this case don't necessarily have to be associated with heights. Maybe what we could do is, for every like vertex that has a random value of like between 0 and 0.5, then we'll say, hey, this is like a hostile like environment. This is like maybe we'll call it like a fire mountain or something, and it'll have different properties. But if it's like 0.5 to 0.75, then it'll be a neutral mountain that doesn't really do anything. But if it's 0.75 to 1, then it'll be like some sort of like holy shrine. And so what we can do is use these randomized values and discretize them in order to get some sort of like biome system going. And while I'm not quite going to show that on this terrain, I can kind of show the idea of discretization, it's a hard word, um, using our texture real quick. So we'll just return to this texture. And, as we mentioned earlier, we have this texture and we can kind of scale it so that, we see this stuff. But what if this isn't that interesting? What if we actually only want three possible values to represent like some sort of map, and the map is like um, I don't know, blue for water, red for lava, and then uh, green for land or something. So what we can do here is we can kind of use this Perlin sample. We're going to double back to the first script we made and use this Perlin sample in order to generate different colors um, that don't directly use the Perlin sample, but use some sort of preset based on what the Perlin sample is. So if that's a bit too confusing, I'll just type this out. If Perlin noise, if Perlin sample is less than 0.25f, then let's go ahead and return color dot red. Um, else if Purlin sample is less than 0.75f, not packages. Return color dot red, or sorry, color dot green. And else, we're gonna go ahead and return color dot blue. Don't forget your semicolons. And we'll comment this one out real quick. And let's just go ahead and check out what this does. Ooh, does not look pretty on the eyes, but it'll get the general idea there. So as you can see here, the majority of the stuff is going to be green. However, by discretizing the values into bounds, um, our values or our bounds are 0 to 0.25, 2.5, 0.25 to 0.75, and then 0.75 to 1. And that allows us to create kind of these biome systems where if it's between a sort of random value, then we'll say, hey, this region is controlled by red or controlled by blue or controlled by green. Uh, I chose green to be the biggest one of the biggest range so that there's mostly like neutral ground. But like you can imagine how you could kind of play with this to create like some sort of biome system. And again, you could like offset it such that like we've never seen this or this mysteriously foot-shaped lava pool. If you turn your head, that's okay. Anyways, um, and we've never seen this before, and it's a new biome generation. And based on the Purlin noise values of this range, we say, hey, it's controlled by red, so now it has these different properties. And so the Purlin noise doesn't have to be directly utilized as the actual Purlin noise value itself as like a height or something, but it can be used to separate the region of your world into separate like biomes, such as this. So yeah, that's just some food for thought. Maybe you can use that to kind of create your own little Minecraft or something. But yeah, that's all I'm gonna have for this tutorial. Thank you.